So let's start talking about our last topic, which is the logistic equation. So last time we talked about exponential growth. Today it's the logistic equation, which is kind of taking the exponential growth topic one step farther. Both of these topics of last lecture and of this lecture are pretty useful in the biological sciences, actually. I was thinking about how a lot of you are bio majors, and actually there's a lot of applications of this to biology. So I mentioned some last time. I'll mention some more today. Let me remind you of basically the main thing that we learned last time. So recall the exponential growth equation that we were studying in the last lecture. That was where P prime was some constant times P. Okay, and P was the population at time T. K was some constant, also called the relative growth rate. But the point is, it was a constant. Maybe one of the confusing things about these differential equations is keeping track of which are the things that are constants and which are the things that are functions. So K was a constant. And the solution, as we discovered, was given by the following. It was that P of T was P naught E to the KT, okay, where P naught was the initial population, the population at time 0. So that's all review from last time. And I had these pictures of, populations that grow. And you can see, for example, the population of the Earth. The human population on the Earth appears to be following this an exponential growth, an exponential curve, as indeed the solution turned out to be. So I'm going to talk about this data a bit more today. In fact, let me do an example with it. So this chart right here shows the population of humans on planet Earth over the course of the last few hundred years. Let's suppose that we're going to measure time in centuries starting at 1800. And, P of T will be the population measured in billions at time T. You can see from this graph here that in the year 1800, the population was about 1 billion. So that's where we get this initial condition from. You can also see from the graph that in the year 2000, the population was about 6 billion. So that's where we get this data point from, because that's 2 centuries after 1800. So let me now find the population at time T. Using what we know is, sorry, I'm just checking something real fast. Let's use the solution that we already found from last time and write down, okay, so P of T is P naught E to the KT, and P naught is given, I just said that the way that we are setting up this model, the initial population is 1 for 1 billion. Moreover, we have a second data point about the population in the year 2000. So 6 is P of 2, which apparently is 1 times e to the k times 2. I could solve this equation for k if I wanted to, although it's actually not necessary. It turns out to be a little bit more convenient for my purposes to just find what e to the k is. So that's what I'm going to do, right? Because e to the 2k is 6, i.e. e to the k squared is 6. So e to the k is, let's see, if I take this equation and like raise both sides to the 1/2 power, I can find what e to the k is, and I see that it is 6 to the 1/2. So maybe you saw I posted an announcement like 20 minutes ago with just a list of exponent properties, because they're going to come in handy in this lecture. For example, as they just did. Anyway, I can now write down that p of t is, let's see, it's 1 times, well, it's e to the kt, which can be written as e to the k in parentheses to the t, or 6 to the 1/2 to the t, or 6 to the t over 2. So I just found the population at time t. We can use this now to, say, predict what the population will be, at any other time. Oh, and by the way, notice this graph right here of what our population as a function of time looks like. It's an exponential graph. This is an exponential function. So in particular, let me find the population in the year 2100. So that's about 80 years from now, 79 years from now. In the year 2100, t is equal to 3, and p of 3 is, let's see what the predicted population is in the year 2100. 6 to the 3/2. So that's about 14.7 billion people are predicted to be on planet Earth, according to this model, in the year 2100. That's a lot, okay? Right now we've got coming up on 8 billion, I think. So like, if you think traffic's bad now, wait till there's 14.7 billion people. So you can see that we are headed towards overpopulation at this rate. Right? This is not good. At some point, we're going to start running out of space, energy, clean water, etc. So this model is not realistic, because obviously this cannot continue indefinitely. Look at the graph of the population. It blows up like unboundedly. Eventually, there's not going to be enough physical room for all these people on the planet. So this model is not realistic, like indefinitely, not for all time. There has to be some upper limit, and that's actually what today's lecture is about. It's about a modification to the model, where we suppose that there's actually some upper bound called the carrying capacity of the population. Any questions so far? Yeah, I see Nicholas is mentioning China's child laws. So that would be an example of something that might start slowing the population down once it starts reaching some certain value that's too large. So how about let's suppose now that Earth has a maximum population, I'm just going to say, of 20 billion. And we're going to call this the carrying capacity. And remember, I'm measuring things in billion. One second. Okay, so I'm now going to propose a new model. The old model was that P prime was KP. I'm going to now modify this model, and I'm going to add an extra term, which is going to slow down the rate of population growth as we approach the carrying capacity of 20. Now, there's maybe multiple ways which you could enact this restriction, but the way that I'm going to do it and the way that they do it in this model is by multiplying by this term of 1 minus P over 20. Okay, so I just modified the standard exponential growth model by adding this extra term. This equation is called the logistic growth equation. And I'll write it down in more generality later. But for now, let me try to solve it. Is it separable? Look at the participant screen so I can see what you all say. Yeah, so yes or no? This equation is separable. And just to remind you, P is P of T. K is just some constant. 20 is obviously a constant. It's the carrying capacity. So, okay, yeah, I got some mixed responses there. The correct answer is that yes, it is. It is separable. So I can solve it. So now let me do that. And this is going to take a minute. I have a bunch of yes or no questions that I'm going to be asking you throughout. So maybe be ready to respond. Okay, yes, so I'm going to solve this. First, I'm going to take care of the constant cases. So first, what if the right side is 0? Okay, so if K times P times 1 minus...
How was it?
times 1 minus P over 20 is 0. Then we get two solutions, right? Then either P is 0, which is a constant, or 1 minus P over 20 is 0, i.e. P is equal to 20. Okay, so P equal to 0 or 20 are the two constant solutions. And we just have to kind of get rid of those at first so that I can then divide them out. So this is just a technical detail which we have to take care of first. Recall, of course, that if you have a constant, then the derivative is 0. So both sides of this equation are 0 for those constant solutions. So now let's assume that P is not 0 or 20. Okay, so let's take the equation dp dt equals k times p times 1 minus p over 20. It's a separable equation. I am now going to separate the variables. I need to get all the p's to one side, all the t's to the other. So let's divide both sides by p, 1 minus p over 20, p, 1 minus p over 20. And let's also multiply both sides by dt. So now I can cancel out. Some factors, and my new equation says that dp over p1 minus p over 20 is k dt. I now have all my p's on one side of the equation. So what's it now time to do?
Integrate.
Good. I can now integrate both sides. Okay, so let's just put an integral sign in front of both sides. The right side is easy to integrate. That's k times t plus some arbitrary constant. Let me ask someone. I'm also going to ask you some questions. Maybe someone who hasn't said anything yet. How can we integrate this term?
U subs?
Okay, I like that, except I don't think I have a good dp on top because of the two factors of p in the bottom. Any other ways that might work? U sub could work, but I'm going to do something more direct. It's like one thing times another thing in the denominator here. What integration?
Always a partial fraction. The partial fraction expansion. I can't talk.
Yeah. So this is amenable to partial fractions. So all those techniques that we learned, so many weeks ago, we now get to apply them. So this is kind of cool. We get to see a useful application of partial fractions. So let's use the partial fraction expansion on that term on the left. So let me expand it. 1 over p times 1 minus p over 20, I think I'm going to multiply top and bottom by 20 to write this as 20 over p times 20 minus p. And this is now, well, it's got two factors in the bottom. So let's write one fraction for each factor. One for a over p, and another one for the 20 minus p term. And right, so this is the partial fraction decomposition, the partial fraction expansion. And I can now solve for the factors a and b. Hopefully you remember how to do this, but I'll just show it here. 20 minus p plus b times p equals 20. And actually, I think in the interest of time, I'm just going to skip to the answer here. So you can check some of the details here. I'll just tell you what a and b end up being. A ends up being 1 and b ends up being 1. Okay, so that's via the method of partial fractions. Again, you can go and check that yourself, but I'm going to skip those details. They're not that hard anyway. So 1 over p times 1 minus p over 20 is 1 over p plus 1 over 20 minus p. Okay. So now that I've performed the partial fractions, I can do the integration here. So the integral of this will be the integral of these two terms. All right, that, if you recall, that's the beauty of partial fractions, is now we can integrate this. We get ln of p plus ln of 20 minus p. Back, yes or no? Is that equal? Is that equality correct? Yes or no, folks? Ooh, man, I got some good yes or no questions today. It's like split right down the middle. So yeah, correct answer is no. There's a mistake right there. That should be a plus. Sorry, that plus should be a minus sign. Yeah, so threw a mistake in there. So that should have been a minus right there. This is what it should say.
Wait, quick question. Is that the only thing that's wrong with this?
Oh, were you thinking of the plus constant plus c?
No, because like I thought the lnp and ln 20 minus p was right, and then like it's wrong. Like, wait, why is it wrong? And then
those now it's correct. I fixed it.
Okay, just making sure. Thank you.
Yeah. What was wrong was I had a plus sign. So the plus sign was wrong. It should have been a minus sign because of the minus here. Okay. You know what? Here, let's ask another yes or no question. Tell me if this is correct. Is this equal to ln of p over 20 minus p? Yes or no? Oh, good. Okay. Yes, most everyone is getting that. That yes is correct. Good. Okay. So what do we have? Remember, on the right-hand side, originally we had kt plus c. So ln of p over 20 minus p equals kt plus c. That's where we're at right now. Do you think that we can solve this equation? Let's make this a yes or no. I want to see if this can be solved. for P. Usually, right, we like to solve for the variable, but sometimes we can't, and we just have to leave it implicit. So yes or no, this can be explicitly solved for P. Everyone's saying, a lot of people are saying no. In fact, everyone's saying no. So yeah, it doesn't look very hopeful. But let me not be swayed or dissuaded, right, from attempting. Let me at least try, and we'll see. Okay, so I'm not going to answer this one yet. Let's find out. The way that we solve for something that's inside a log is like we take e to the power of both sides. Okay, so it's like e to the power of this whole thing is e to that whole power. And on the left, the e and the ln kind of cancel each other out. So on the left, we're going to get absolute value p over 20 minus p. And on the right, it will be e to the kt plus c, which, as you've seen, as I've done a few times before, we can also write as e to the c times e to the kt. So let me get rid of the absolute values. I can ditch the absolute values at the cost of a plus or minus sign. All right, so in case you aren't sure how or why I did that, that's using the fact that like if the absolute value of one thing is another, then A must be plus or minus the other thing.
Wait, do you need the c raised for in the exponential and in the kt plus c?
Yeah, that's what I was about to ask.
Oh, yeah, you're right. Thank you. Extra c there. Cool. Now, let's see. I think I'm going to do what we usually do and give this variable a different, give this constant a different name. It'll make things a bit easier. So let's call this, how about capital B? So this whole thing is equal to B, E to the KT. Okay, so P over 20 minus P is BE to the KT. Let me multiply both sides by 20 minus P. P is BE to the KT times 20 minus P, which is equal to 20 BE to the KT minus P BE to the KT. And let me move all the P's to one side of the equation, okay? Because P is equal to this. So if I like add this term to both sides, PBE to the KT plus P is equal to 20 BE to the KT. Any questions on that? okay, i.e., I can pull out a p. I'm left with b e to the kt plus 1 equals 20b e to the kt. Oh, wait a second. I can get p by itself right now. So I just divide both sides here by, b e to the kt plus 1. B e to the kt plus 1. And p of t is 20 b e to the kt over b e to the kt plus 1. Wow. All right. So apparently I am able to solve that equation explicitly for p. And I'm not quite done cleaning it up. So typically we'll make this look a little bit simpler by, let's see what we're going to do. Let's multiply top and bottom. I'm going to divide out the b and also the kt term. Okay. So top and bottom. So I get some cancellation on the top and on the bottom. And what do I get? Let's see, on the top, I just have a 20. On the bottom, I'm going to get 1 plus 1 over b e to the negative kt. And finally, apologies, I'm going to introduce yet another letter to make this look even simpler. And I'm going to call this a. Okay? So a is 1 over b. Again, still just some constant. And this whole thing is equal to 20 over 1 plus a e to the negative kt.
How does the negative e, or sorry, the e to the negative kt cancel out with the e to the kt? Doesn't that leave like some sort of negative or something?
Because you get, well, e to the kt times e to the negative kt.
Oh, wait, it's the fraction. I forgot. Technically
1.
speaking. Yeah.
So cool. We found our answer, right? So p of t is 20 over 1 plus a e to the negative kt. And we have solved the logistic equation. Whew, okay, that's the hardest thing I wanted to do today, the long derivation. I think now that I've done it for this particular carrying capacity, right? I did it for the carrying capacity being 20. I'll just give you the equation for general carrying capacity. So I already printed that out. Where is it? There we go. Okay, so here's your logistic equation. Again, so this is just the same deal that I just did, except using m instead of 20. And again, if p is the population at time t, m is a constant, which is equal to the carrying capacity. K is some other constant, which is also called the growth rate. Then this is the logistic differential equation. And this is the solution. Okay. So, I'm not going to go prove those formulas because I basically just did it. And yeah, that's our new thing. So any questions? Sorry, give me a second. All right, so
How do you
let's take,
come up with like the differential equation?
how did we come up with it?
Yeah, like, because
That's
you
a good
have to.
question. Yeah, that's a really good question. It was kind of ad hoc, right? So my explanation, and probably the best one that you're going to get right now, is we just threw on an extra term that would make the rate of change go to 0 once you hit some maximum carrying capacity. And here, you know what? Let me show you the slope field. I think that will. Oh crap! I already did that. I think that will clear things up a little bit.
I don't know, because just part of me is wondering, like, why have the differential if you can just have like the P of t, if that makes sense.
Why have the differential equation if you can just know the answer?
Yeah.
That's a good question. I guess, you know, in this case, in this particular narrow set of circumstances, you could just jump right to the answer, but we're trying to prepare you for a more general set of circumstances. So now, like in theory, you could come up with your own differential equation. And most of them cannot always be solved so neatly in such a closed form. The book actually has some modifications of the logistic equation. So you can see some examples of how you might modify this problem in the book. And unless you know like where the differential equation comes from, you're not going to know how to modify it either. So that would be one answer to your question. I think that's a very good answer. There's probably even more answers to your question than the one that I just said, although I don't have any other good ones off the top of my head. Although I think the one, like I said, I think the answer that I did give is already a pretty good answer. So let me show you a picture of that solution. This is the solution that I'm talking about. If I graphed it, we would get this shape right here, okay? There's actually a name for that shape. It's called a sigmoid. Well, let me say that more carefully. It's an example of a class of shapes that are called sigmoids. So this is an example of a sigmoid, and it's also called an S-curve. You can see how it gets the name S-curve, right? Like it kind of looks like an S, kind of, a little bit. So another function that you could also call sigmoidal might be tan inverse. Tan inverse also has that same sort of shape. Here's a property of the graph. It has horizontal asymptotes, right? So like it approaches the carrying capacity asymptotically, never actually reaches it though. So in no finite amount of time will, for example, the Earth's population ever actually equal 20 billion, but it'll get arbitrarily close according to this model. And as I said at the beginning of this lecture, there's a lot of applications of logistic growth models and or sigmoids, like for example, learning curves. So let's say you're trying to learn something like how to play the violin or archery, or even if you're lifting weight, then your progress often follows an S-shaped curve in that you make a lot of progress at the beginning. So at first you're getting a lot of gains, but then it starts slowing down, and eventually you have to put in like a lot more practice to just get just a little bit better once you pass the sort of beginner phase. So learning curves are an example of that. Another one might be molecular concentrations. So, for example, the concentration of hydrogen ions or hydroxide ions, which is how you measure the pH that's used in chemistry or pharmacology or biochemistry, pretty much concentrations of almost any molecule or chemical often follow these sigmoidal curves. Salt concentrations, for which have application to agriculture, for example, is another one. Sigmoids come up in neural networks and signal processing because, for example, let's say you have an on-off signal where here it's off and now it's on, right? Like in neural networks or in signal processing, they both have bits that are either on or off. Well, it's often more useful to sort of smooth that out into an S-shaped curve. So sigmoids are used there as well. Okay. I mentioned the slope field, and this sort of ties into what Michaela was asking. So here's a picture of the slope field for the differential equation P prime equals P1 minus P over 2. Okay, so K is 1 and M is 2. A couple of features I want to point out on this graph is the horizontal asymptote at the maximum carrying capacity of 2, and another one at 0. And if you start anywhere between 0 and 2, all the solutions have this same shape, right? They'll all approach like 0 asymptotically in negative infinite time and approach the carrying capacity as time goes to positive infinity.
This might sound like really morbid, but technically, if a population goes extinct, wouldn't you be crossing the like bottom asymptote?
Yeah. So the dodo population, right, apparently includes a point where it actually hit the 0 population mark.
Does that mean that there's like a specific hole in the asymptote where you can like cross it? Because I know that some functions there's a case where that's possible, but I'm like, is that the case for logistic curves?
Well, you can argue about the validity of the model. Like for one, with populations, typically populations occur in discrete numbers. You know, like technically you can't have half a person or a quarter or a third or root 2 of a person. So you could argue that maybe like once the population goes below the number 1/2, you're less than half a person, and that rounds down to 0 people. So that might be one way that you could fix the model to handle that. But yeah, all of these all fall under the headline of mathematical modeling. So it's all mathematical models that approximate some real world scenario. And arguing about how valid they are is a very valid argument, and there's a lot of debate about it. Typically, you always have to trade off accuracy versus simplicity. So you could handle it more, accurate considerations, but that makes the model more complicated. And what we're showing you here now in this class is pretty much like the simplest the models can get. So finally, let's see what happens on Earth now if we incorporate the logistic model. Right, because at the beginning of the class, I used the exponential growth model. And let me just remind you that with the exponential growth model, what was it? We found that 14.7 billion was going to be the population in the year 2100, according to the exponential growth model. Well, now let's redo the calculation using the logistic growth model. So that's example 2 here. It's the same setup, but just use the logistic model instead of the exponential one. You can ignore question 2 because we're not going to have time for it. But again, we'll suppose the population of the Earth now obeys a logistic model, but the carrying capacity is 20 billion people. Again, as before, T is number of centuries after 1800. Again, same conditions. It was 1 billion in the year 1800. It was 6 billion in the year 2000. Let's find the population in the year 2100, i.e., we want to find P of 3. And I want you all to do this. So go ahead and start it. I'll give you some hints. Right off the bat, though, let me just ask, do we expect it to be more or less than 14.7? So yes or no, we expect our answer to be more than the one we got with the previous model, yes or no? Oh, good. Okay, yeah. So good. Everyone's correctly getting that. No, it should be less because this. In fact, the whole point of this model was to fix the problem that the other one predicted numbers that were too big. So why don't you go ahead and try to find what P of 3 is, and some hints to help you are, well, for one, I gave you the equation already. So just use the given P of T. And apparently M is 20. Here's another hint. How about you first find A using P of 0. Then, and this is going to be the hard part, then find e to the negative k. Using P of 2 equals 6. That one is going to be kind of ugly.
How do you know which point to like attribute it to?
Attribute what to?
How do you know to attribute P of 0 to A?
I didn't. It's a way that you can solve it. And it ends up being easier than doing things in a different order. But yeah, A is not like the initial population. It's easy plugging in 0 because the K disappears, as you'll see. And if I can get some right answers, let's say 5 people can get it right, I'll show you a picture that's 1 room, but it looks like 4 rooms. Or 1 picture, but it looks like 4 pictures. Yeah, it's 1 picture, but it looks like 4 pictures. Oh, somebody asking about psych and neuroscience application. Oh, good question. Probably come up with some psych and neuroscience application. can private message me if and when you think you got it.
Are we supposed to be getting like actual values for A or another equation?
I think you'll need an actual value for A and probably for e to the negative k as well. Note that you could find k, but it's not really necessary. So I get you started like p of 0 is 1. So that's, oh, here, let me write down p of t is apparently 20 over 1 plus a e to the negative kt. And 1 is p of 0 is 20 over 1 plus a e to the, well, k times 0. So a, oh, nice, Edward. Yeah, Edward got it. That's good. He was 19, apparently. And we're done, by the way. So if and when you finish, you can go. There's nothing else that we're going to see, except this. I want to see a cool picture. Six is p of 2. 21 plus a e to the negative 2k. So 1 plus, oh, which is actually 20 over 1 plus 19 e to the negative k squared. So 20 plus 19. Oh, yeah, Jared, that's pretty close, Jared. I guess you probably rounded, so maybe that's why it's not exactly what I have, but I think that you might have done it right, because it's pretty close to what I got. This is or sorry, 20 over, what am I doing here? So, 7 over 19 times 0.34, Michaela. What are you predicting, like nuclear war? Holy crap.
No, I don't know what happened. I distributed the 6 to the denominator, and then I thought that I did my math right. Clearly not, because I don't know what happened.
Okay, well, here's my e to the negative k. As I mentioned, you don't actually have to find k. Like you could if you want, but you don't have to though. So I'm not going to bother finding it. Like it turns out, this is it's sufficient to just find what e to the negative k is, because then p of t, I can now write down exactly what it is. So it's 20 over 1 plus 19. Let's see. And then 7 over 19.3 to the 1. Yeah, see if I did that right.
Wait, I'm actually kind of confused. I don't know where I went wrong because I distributed the denominator, or like I multiplied 6 by 1 plus 19 e to the negative 2k, and then I distributed the 6, and then I subtracted 6 and then divided by 114.
So you had a 20 minus 6,
Yeah.
so 14 over, yeah, well, then you should be able to like cancel cancel some stuff. So what did you have for e to the negative k?
I got, wait, what? I got that like 0.3 number. Was I supposed to cancel with a negative 1/2?
Oh, well, so then you're not, that might be, yeah, that might be e to the negative k. Yeah, but okay, how about the population then though? So
Wait,
so
was
that,
it?
okay, maybe that was right, but I want to find what the population is, what P of 3 is, what the population in the year 2100 is.
Oh my God, I forgot to plug it back into the
Yeah.
equation. Okay, there we go.
Oh, Carlos, that looks good, Carlos. Nice. Nicholas got it. One other person has to get it, I think. 1, 2, 3, 4. Ooh, 11.002. All right. So, yeah, about 11, let's just say 11 billion. Okay, so notice it's less than 14.7, right? Because like the exponential models go like this, the logistic ones go like this. So it makes sense that it was less than the other one. Cool. Okay, cool. That's it, folks.